Hey fellow nerds, today we are going to learn Z transform. We'll be covering Z transform, relation between Fourier transform and Z transform, region of convergence of Z transform, properties of region of convergence, and inverse Z transform. Let us start by having a recap on how we represented discrete time LTI systems in different domains. In the time domain, if the input is x of n, output is y of n, and the impulse response of the system is h of n, we wrote y of n is equal to the convolution of x of n and h of n. In the frequency domain, we took if the input is x of e raised to j omega, output is y of e raised to j omega, and h of e raised to j omega is the frequency response of the system, then y of e raised to j omega is the product of x of e raised to j omega and h of e raised to j omega. Here x of e raised to j omega, y of e raised to j omega, and h of e raised to j omega are the discrete time Fourier transforms of x of n, y of n, and h of n. So the frequency response of this system, h of e raised to j omega, can be related to the impulse response h of n like this. Summation from n equals minus infinity to infinity, h of n e raised to minus j omega n. Now, if we take z equals e raised to j omega, we can show the same system like this. Input will be x of z, output will be y of z, and the system response will be h of z. In this case, we can write y of z is the product of x of z and h of z. We got this simply by changing e raised to j omega in this equation into z. So we can use this equation over here to write the expression for h of z. H of z will be equal to summation from n equals minus infinity to infinity, h of n. We have e raised to minus j omega n. It is e raised to j omega to the power minus n. So if we take e raised to j omega as z, we can write z to the power minus n over here. This is still Fourier transform. We are just taking e raised to j omega to be z. So in discrete time Fourier transform, if we take z equals e raised to j omega, we can write the magnitude of z is going to be magnitude of e raised to j omega. But according to Euler's formula, we know e raised to j omega is cos omega plus j sine omega. If you take the magnitude of this, it is going to be root of cos square omega plus sine square omega, which is equal to 1. So we can write magnitude of z in this case is 1. Now let us take general values of the complex variable z, where magnitude of z is not 1 anymore, it is r. That is, we take z is equal to r e raised to j omega. So when you take the magnitude of e raised to j omega is still 1. So magnitude of z will be r multiplied by 1, which is r. In that case, we can write x of z for a discrete time signal x of n will be summation from n equals minus infinity to infinity x of n z raised to minus n. This is the same expression, but this time we are taking a general value for z where its magnitude is not equal to 1. Instead, it is something else that is called r. In that case, we can call this z transform of x of n. The relation between x of n and x of z can be denoted by using a double-sided arrow with a z on top of it. Let us now have a comparison between discrete time Fourier transform and z transform. First, let us take Fourier transform. Consider we have a discrete time signal x of n. Fourier transform of x of n can be written in terms of z like this. X of z is equal to summation from n equals minus infinity to infinity x of n z raised to minus n. But this is only Fourier transform if z is equal to e raised to j omega. That is, its magnitude is equal to 1. So we can conclude that Z transform of a signal x of n for z being equal to e raised to j omega or its magnitude r being equal to 1 gives the Fourier transform. So we can write x of z if z is equal to e raised to j omega is equal to Fourier transform of x of n. Now let us go to z transform. For that, let us again consider a signal x of n. We know its Fourier transform x of e raised to j omega is given by summation from n equals minus infinity to infinity x of n e raised to minus j omega n. X of e raised to j omega had e raised to minus j omega n, which is e raised to j omega to the power minus n. What if I want x of r e raised to j omega? Then it will become summation from n equals minus infinity to infinity x of n r e raised to j omega to the power minus n. Or this can be written as r to the power minus n e raised to minus j omega n. Let us replace it by that. Now we know r e raised to j omega is the general expression for z where its magnitude is not 1, it is r. So we can write x of z is equal to summation from n equals minus infinity to infinity x of n r raised to minus n e raised to minus j omega n. Now, when I compare the right hand side of this equation with the right hand side of this equation, the only difference I can see is here I have x of n, here I have x of n r raised to minus n. So, if this is the Fourier transform of x of n, then this should be the Fourier transform of x of n r raised to minus n. So, I can write x of z or z transform of a sequence x of n is nothing but Fourier transform of the sequence x of n r raised to minus n. We had learned a very similar result between the Laplace transform and continuous time Fourier transform. Let us solve a problem now. Well, there are two problems. Let's take the first one. We have to compute the z transform of x of n, which is a raised to n u of n. We know x of z is given by summation from n equals minus infinity to infinity x of n z raised to minus n. But here x of n is a raised to n u of n. Let us replace it. Now we have a u of n. It is 1 only from n equal to 0 to infinity. For n less than 0, it is 0. So we don't really have to take the summation from minus infinity to infinity. We can just take it from n equals 0 to infinity. A raised to n. From n equals 0 to infinity, u of n is 1. So we don't have to write it. Z raised to minus n. We can write it like this. Summation from n equals 0 to infinity a z raised to minus 1 to the power n. Now, this is the sum of a geometric progression. If you give n equal to 0, it is a z raised to minus 1 to the power 0, which is 1. Plus, if you give n equal to 1, you get a z inverse. Plus, if you give n equal to 2, you get a z inverse to the power 2. Plus, it goes up to infinite terms. So, this is an infinite GP. It will converge to a finite value only if the common ratio is less than 1. Here the common ratio is a z raised to minus 1. If the common ratio is greater than 1, then each term will become bigger than the previous term and the sum will only go to infinity. So we have to write for x of z to converge, the common ratio a z inverse should have a magnitude that is less than 1. Or we can write magnitude of a multiplied by magnitude of z inverse is less than 1. Let us take magnitude of z inverse to the other side of the inequality. Then we can write magnitude of a should be less than magnitude of z. Or we can write magnitude of z should be greater than the magnitude of a. Now the sum of a geometric progression whose first term is 1 and common ratio is r is given by 1 minus r. Here our initial term is 1 and common ratio is a z raised to minus 1. So we can write x of z is equal to 1 by 1 minus a z inverse. Or if you multiply the numerator and the denominator by z, you can write x of z is equal to z divided by z minus a. And the condition is magnitude of z should be greater than magnitude of a. Let us go to the next problem. Compute the z transform of x of n. X of n is minus a raised to n u of minus n minus 1. We know x of z is given by summation from n equals minus infinity to infinity. X of n here is minus a raised to n u of minus n minus 1 z raised to minus n. We have a negative here. Let us put it over here. Now we have a u of minus n minus 1 here. It is 0 for every n that is greater than or equal to 0. It is 1 for every n that is less than or equal to minus 1. So we don't have to take summation from minus infinity to infinity. Instead, we can take minus summation from n equals minus infinity up to minus 1. A raised to n. When n takes values from minus infinity to minus 1, u of minus n minus 1 is 1, so we don't have to write it. Z raised to minus n. Since the summation is from minus infinity to minus 1, it is difficult for us to use the expression to find sum of a GP. So let us do a trick. Take m is equal to minus n. Then x of z becomes negative summation n equals minus infinity, then m will be plus infinity. N is minus 1, then m will be plus 1. So we can write m equals infinity to 1. But this is summation. We know the order doesn't matter. You can add 1 plus 2 plus 3, or you can add 3 plus 2 plus 1. So instead of writing summation from m equals infinity to 1, let us write summation from m equals 1 to infinity. A to the power n will become a to the power minus m. Z to the power minus n will become z to the power m. Now we know it doesn't matter what we call the variable to which we are giving the limit, which is m here. I am going to call it n itself. We have a raised to minus n, z raised to n. We can write it like this: a raised to minus 1, z the whole raised to n. Now this is a geometric progression. So we can write it like this: negative of, if you give n equal to 1, it is a to the power minus 1 z, plus if you give n equal to 2, it is a to the power minus 1 z squared, plus it goes on like that. There are infinite terms, so it is an infinite GP. Now for the sum of an infinite GP to converge, its common ratio should be less than 1. Here the common ratio is a raised to minus 1 z. So we can write, for x of z or the sum of the GP to converge, the magnitude of the common ratio, magnitude of a raised to minus 1 z, should be less than 1. Taking magnitude of a inverse to the other side, we can write magnitude of z should be less than magnitude of a. Now here we have a GP whose first term a is a inverse z, and its common ratio r is also a inverse z. When the first term of a GP is not 1, we take its sum to be a divided by 1 minus r. So here we can write x of z is equal to, there is a minus here, so we have to put it, minus of a is a inverse z divided by 1 minus r is a inverse z. Let us multiply it with a z inverse and divide it with a z inverse. Then the numerator becomes negative of a inverse z multiplied by a z inverse is 1 divided by 1 multiplied by a z inverse is a z inverse minus a inverse z multiplied by a z inverse is minus 1. There is a negative over here. Let us include it over here and write it as 1 minus a z inverse. So we get x of z is 1 by 1 minus a z inverse if magnitude of z is less than magnitude of a. Now, if we multiply the numerator and denominator of this expression by z, we can write x of z in a different way. Z divided by z minus a. Again, the condition is magnitude of z should be less than magnitude of a. So for the sequence a raised to n u of n, we got the z transform 1 by 1 minus a z raised to minus 1 or z by z minus a. For the sequence minus a raised to n u of minus n minus 1, we got the z transform 1 by 1 minus a z inverse or z by z minus a. They both have the same rational function as z transform. The difference is in the condition. Here magnitude of z should be greater than magnitude of a. Here magnitude of z should be less than magnitude of a. From solving these two problems, we can conclude that z transform of a sequence does not converge for every value of z. In fact, the range of values of z for which the summation converges is called the region of convergence of the z transform. We know z transform of a sequence x of n is the same as Fourier transform of the sequence x of n r raised to minus n. So we can define region of convergence in a different way using this. Region of convergence or ROC consists of the values of z being r e raised to j omega for which the Fourier transform of x of n r raised to minus n converges. If the Fourier transform of x of n r raised to minus n converges to a finite value, then z transform of x of n converges to a finite value because they are equal. Let us now figure out the condition for convergence of z transform. When we say x of z converges, what we mean by that is that the magnitude of x of z is finite. Magnitude of x of z is magnitude of summation from n equals minus infinity to infinity x of n z raised to minus n. Here I have taken magnitude after taking summation. If I take summation and then take the magnitude, the only thing I'll have to change is that instead of equals, I'll have to write less than or equal to. We have taken z to be equal to r e raised to j omega. Let us replace z over here by that. Now, this can be written as r raised to minus n e raised to minus j omega n. Let us replace it with that. This is the same as taking summation from n equals minus infinity to infinity magnitude of x of n r raised to minus n multiplied by magnitude of e raised to minus j omega n. But according to Euler's formula, we know e raised to minus j omega n is cos omega n minus j sin omega n. If you take the magnitude, you will get 1. So magnitude of e raised to minus j omega n is 1. So we can just remove it. That means magnitude of x of z will always be less than or equal to summation from n equals minus infinity to infinity magnitude of x of n r raised to minus n. Therefore, the condition for x of z to converge or magnitude of x of z to be finite is that summation from n equals minus infinity to infinity magnitude of x of n r raised to minus n should be a finite value. If this is a finite value, then this is a finite value. If that is a finite value, then x of z converges. Let us write it down. For x of z to converge, summation from n equals minus infinity to infinity magnitude of x of n r raised to minus n should be a finite value. In other words, we can say x of n r raised to minus n, that is what we have over here, should be absolutely summable. When we say absolutely summable, it means the summation should have a finite value. Which means ROC will contain all the values of R for which x of n r raised to minus n will be absolutely summable. So what does that mean? This gives us a very important result, which is ROC is independent of omega. ROC only depends on the values of R. This is very similar to Laplace transform where ROC did not depend on omega, instead it only depended on the values of sigma. These are the results we got from the last two problems we solved. For a sequence a raised to n u of n, we got the z transform to be z by z minus a, ROC being magnitude of z greater than magnitude of a. But magnitude of z is r, so we can write r greater than magnitude of a. We could also write it in a different way. Instead of z by z minus a, we could also write 1 by 1 minus a z inverse. For another sequence minus a raised to n u of minus n minus 1, we got the same z transform z by z minus 1 with one condition. ROC is wherever magnitude of z is less than the magnitude of a. We could also write it in a different way. Instead of z by z minus a, we can also write 1 by 1 minus a z inverse. So we can make two observations from these. The first thing is algebraic expressions for the z transform is identical for both signals. But the set of values of z for which the expression is valid is very different. So we can make the conclusion that both the algebraic expression and the range of values of z for which the expression is valid are required to specify a signal. To specify a signal in the z domain, you have to have the algebraic expression and also the range of values of z for which the expression is valid. That is the region of convergence. So we can conclude that just as Fourier transform does not converge for all signals, Z transform may also converge for some values of R and then not for other values. Let us now see how we can represent region of convergence of Z transform. Z is taken to be R e raised to j omega. Using Euler's formula, we can make it into this R multiplied by cos omega plus j sin omega. Or we can write R cos omega plus j R sin omega. Here R cos omega will be the real part of z and R sin omega will be the imaginary part of z. Let us make a plane by taking the real part of z on the x-axis and the imaginary part on the y-axis. We can call this the z-plane. Consider a point in the z-plane over here. Let us draw a line that joins the point to the origin. Let us assume that the angle this line makes with the x-axis is omega. And the magnitude of the line is r. In that case, its x component is going to be r cos omega and the y component is going to be r sin omega. That means the coordinates of this point are r cos omega and r sin omega. So we can say this represents z equals r e raised to j omega. Now let us draw a circle that is centered at the origin of the plane and whose radius is r. If I take a point over here, I can still call it z equals r e raised to j omega because its magnitude is still going to be r, but for a different omega. So every point on this circle can be taken as z equals r e raised to j omega. R is the same for all of them, but omega takes any value from 0 degrees to 360 degrees. But in all those cases, magnitude of z is going to be magnitude of r multiplied by magnitude of e raised to j omega. Omega can take any value, but magnitude of e raised to j omega is always going to be 1. So in all these cases, that is for all the points on this circle, magnitude of z will be equal to magnitude of r, which is r. Now let us take a circle on the z-plane whose radius is equal to 1 unit. We call this the unit circle. Now we know that Fourier transform of a sequence x of n is equal to z transform of the sequence x of n if r is equal to 1. That means if r equal to 1 is included in the ROC of the z transform, then the Fourier transform of x of n exists. If r equal to 1 is not included in the ROC, then the Fourier transform of x of n does not exist. So we can conclude that for Fourier transform of a signal x of n to converge, R equal to 1 should be included in the ROC of its Z transform. If R equal to 1 is included, that means in the ROC the unit circle should be included. So we can conclude that for the Fourier transform of a signal x of n to converge to a finite value, the unit circle should be included in the ROC of its Z transform. Let us take an example. I'll take the signal a raised to n u of n. We already found its Z transform. It is z by z minus a, and ROC is magnitude of z should be greater than magnitude of a. We can see that the denominator will become 0 if z equal to a. So z equal to a is a pole of x of z. Also, when z equal to 0, the numerator will become 0. So 0 is a 0 of x of z. So x of z has a 0 at z equal to 0 and it has a pole at z equal to a. Let us take the z plane and mark z equal to 0 and z equal to a as a 0 and a pole. In the first case, I'm going to assume that magnitude of a is between 0 and 1. So I will mark a over here. We can take all points on the plane where the magnitude of z is a. It doesn't matter what omega or the angle is. So that means we can take every point on a circle whose radius is a. That means we can take all the point on the plane where the magnitude of z is greater than a. So it will look like this. We can take anywhere except inside this circle. Now, if we consider magnitude of A is greater than 1, the ROC is going to look like this. In the first case, since A is less than 1, the unit circle is included in the ROC. In the second case, since A is greater than 1, the unit circle is not included in the ROC. So in the second case, since the unit circle is not included, its Fourier transform is not going to converge. That is, if magnitude of A is greater than 1, the Fourier transform does not converge, but the Z transform does. Let us now solve a problem based on what we learned. We have to find the Z transform of x of n, which is 7 times 1 by 3 raised to n u of n minus 6 times 1 by 2 raised to n u of n. Let us use the result that we learned. Z transform of a raised to n u of n is 1 by 1 minus a z inverse, and magnitude of z should be greater than magnitude of a. Using linearity property, we can find the z transform of both these terms separately. So we can write x of z is going to be 7 times. Here we have 1 by 3 to the power u of n. So a is 1 by 3, therefore its z transform is going to be 1 by 1 minus 1 by 3 z inverse. Magnitude of z should be greater than magnitude of a. So we can write magnitude of z should be greater than 1 by 3. The second term is minus 6 1 by 2 raised to n u of n. So we can write minus 6, a here is 1 by 2. So its z transform will be 1 by 1 minus 1 by 2 z inverse. Here also magnitude of z should be greater than magnitude of a. So we can write magnitude of z should be greater than 1 by 2. So magnitude of z should be greater than 1 by 3. It should also be greater than 1 by 2. So the common region is magnitude of z being greater than 1 by 2. So x of z is 7 divided by 1 minus 1 by 3 z inverse minus 6 divided by 1 minus 1 by 2 z inverse, where magnitude of z should be greater than 1 by 2. If we add both the terms, we get x of z is equal to 1 minus 3 by 2 z inverse divided by 1 minus 1 by 3 z inverse multiplied by 1 minus 1 by 2 z inverse. Now the numerator will become 0 if z is equal to 3 by 2. So we have a 0 at z equals 3 by 2. The denominator will become 0 if z equals 1 by 3 or if z equals 1 by 2. So we have two poles, one at 1 by 3 and one at 1 by 2. Other than these, x of z actually has one more hidden 0. If you give z equal to 0, since we have z inverse everywhere, it will become undefined. So to check that, let us multiply this with z square and divide it with z square. If we do that, we get x of z is equal to, on the numerator we will have z multiplied by z minus 3 by 2 divided by, I'll give 1z to this term and 1z to this term. So that becomes z minus 1 by 3 multiplied by z minus 1 by 2. ROC is magnitude of z is greater than 1 by 2. Now we can clearly see all the poles and all the zeros. We have a 0 at z equal to 0, 1 at 3 by 2. We have a pole at 1 by 3 and another pole at 1 by 2. If we plot the ROC on a z plane, this is how it will look like. We have zeros at 0 and 3 by 2. We have poles at 1 by 3 and 1 by 2. And the ROC is supposed to be every point on the z plane where the magnitude of z is greater than 1 by 2. So it will look like this. It includes the unit circle, so we can say the Fourier transform of this function is going to converge. Let us solve another problem. We have to find the z transform of x of n, which is 1 by 3 raised to n sine pi by 4 n u of n. First, let's use Euler's formula to write sine pi by 4n in this form. E raised to j pi by 4n minus e raised to minus j pi by 4n divided by 2j. If we do that, then we can write x of n in this form. Now we can split this into two terms, so we get 1 by 2j, 1 by 3 raised to the power n, e raised to j pi by 4n u of n minus 1 by 2j, 1 by 3 to the power n, e raised to minus j pi by 4n u of n. Now, e raised to j pi by 4n is actually e raised to j pi by 4 to the power n. Similarly, e raised to minus j pi by 4n is e raised to minus j pi by 4 to the power n. Now here we have 1 by 3 raised to n multiplied by e raised to j pi by 4 raised to n. We can combine them like 1 by 3 e raised to j pi by 4 the whole raised to n. The same way, here we have 1 by 3 raised to n, e raised to minus j pi by 4 raised to n. We can combine them and write 1 by 3 e raised to minus j pi by 4 the whole raised to n. We know using Euler's formula e raised to j pi by 4 is cos pi by 4 plus j sin pi by 4. Cos pi by 4 is 1 by root 2. Sin pi by 4 is also 1 by root 2. So basically e raised to j pi by 4 is 1 by root 2 plus j 1 by root 2. What I mean is this is a constant. Similarly, e raised to minus j pi by 4 will be 1 by root 2 minus j 1 by root 2. So that is also a constant. So that means in both these terms, we can use this entire thing to be our a so that we can use the result that we learned. Z transform of a raised to n u of n is 1 by 1 minus a z inverse, where magnitude of z is greater than magnitude of a. In the first case, this will be our a. In the second case, this will be our a. So we can write x of z is equal to 1 by 2j is also a constant, so let it be there. 1 by 1 minus a is 1 by 3 e raised to j pi by 4 z inverse minus 1 by 2j is a constant. 1 by 1 minus a is 1 by 3 e raised to minus j pi by 4 z inverse. Now in the first case, the magnitude of a is going to be 1 by 3. Why? Because magnitude of e raised to j pi by 4 is 1. In the second case, magnitude of a is going to be again 1 by 3 because magnitude of e raised to minus j pi by 4 is also 1. So for the first term, the condition will be magnitude of z should be greater than 1 by 3. For the second term also, magnitude of z should be greater than 1 by 3. So we can write our final condition. Magnitude of z should be greater than 1 by 3. Now if we add both terms, we get x of z is equal to 1 by 3 root 2 divided by 1 minus 1 by 3 e raised to j pi by 4 z inverse multiplied by 1 minus 1 by 3 e raised to minus j pi by 4 z inverse. Here magnitude of z should be greater than 1 by 3. To see the zeros and the poles clearly, let us multiply the numerator and the denominator by z square. Then we will get this. I gave one z in the denominator to this term, so I got this. I gave the other z to this term, so I got this. We have z square in the numerator. That means there are two zeros at z equal to 0. We have a pole at z equals 1 by 3 e raised to j pi by 4. We have a pole at 1 by 3 e raised to minus j pi by 4. If we plot the ROC on a z-plane, this is how it will look like. We have a 0 at z equal to 0. We have a pole at a point where magnitude of z is 1 by 3 and the line joining the point and the origin is making an angle pi by 4 with the x-axis. That is shown over here. This angle will be pi by 4. We have another pole at a point where the magnitude of z is 1 by 3, but the line joining the point and the origin is making an angle minus pi by 4 with the x-axis. That is shown over here. This angle would be minus pi by 4. Now x of z converges for all values of z where its magnitude is greater than 1 by 3. So that is everywhere on the z-plane except inside the circle whose radius is 1 by 3. Let us now learn some properties of region of convergence. The first one is that the ROC of x of z consists of a ring in the z-plane that is centered about the origin. This is a pretty obvious property, and the reason for this is that ROC only depends on R. It doesn't depend on omega, it only depends on R, which is the magnitude of z. So if R equal to A is included, that means this whole circle is included because all these points on the circle will have magnitude of Z equal to R. Or we can say if a specific value is in the ROC, then all values of Z on the same circle will also be in the ROC. Because at all those points, magnitude of Z will be equal. Let's go to the next property. This one says ROC does not contain any poles. This is the most obvious property because at poles, x of z becomes infinity. The whole idea of x of z being converging is that its value should be finite, not infinite. At every pole, x of z will have infinite value. So x of z does not converge at poles. Therefore, region of convergence can never contain any poles. The next property says if x of n is of finite duration, then ROC is the entire z-plane except possibly z equal to 0 and or z equals infinity. We'll have to check for z equal to 0 and z equal to infinity. This is because we take x of z to be summation from n equals minus infinity to infinity x of n z raised to minus n. But if the signal is finite duration, let us assume that the signal only has non-zero values from n1 to n2. Then instead of taking summation from minus infinity to infinity, we can simply take it from n1 to n2. The upper limit is n2, which is a finite value. The lower limit is n1, which is also a finite value. So the summation is going to always converge to a finite value. Except when the magnitude of z becomes 0 or infinity, which we'll have to check ourselves. For example, let us take n1 is less than 0 and n2 is greater than 0. First of all, this is how we write x of z. If you open the summation, you get x of z is equal to x of n1 z raised to minus n1 plus x of n1 plus 1 z raised to minus n1 plus 1. It goes like that up to x of n2 z raised to minus n2. Since we are taking n1 to be negative and n2 to be positive, the summation will include both positive and negative powers of z. When n is negative, z raised to minus n will have a positive power. When n is positive, z raised to minus n will have a negative power. So the summation is going to include both positive and negative powers. In that case, when magnitude of z becomes 0, the terms will become unbounded. For example, let us say we have z raised to minus n is equal to 2. Then it will become z raised to minus 2. Or we can write 1 by z raised to 2. Now, if magnitude of z is 0, this becomes 1 by 0 or unbounded. So z equal to 0 cannot be included in the ROC. Again, when magnitude of z tends to be infinity, the terms with positive powers will become unbounded. For example, let us say we have z raised to minus n is equal to minus 2. So it becomes z raised to 2. Now, if magnitude of z tends to be infinity, this will be infinity squared, which is again unbounded. So z equal to infinity can also not be included in the ROC. Therefore, we can conclude that if the signal ranges from a negative value to a positive value, then its ROC will contain the entire z-plane but not z equal to 0 and z equal to infinity. Let us take a second case where n1 and n2 are both greater than or equal to 0. N takes every value from n1 to n2, but n1 and n2 both are positive. So the value of n is always going to be positive, which means the value of minus n is always going to be negative. So the summation will include only negative powers of z. In that case, when the magnitude of z becomes equal to 0, the terms with negative powers will become unbounded. We will get 1 by 0, which is unbounded. So z equal to 0 cannot be included in the ROC. Let us take a third case where n1 and n2 both are negative. Summation is from n equals n1 to n2, but n1 and n2 are both negative. So the value of n is going to be always negative. The value of minus n is always going to be positive. So we can say the summation includes only positive powers of z. In this case, when magnitude of z becomes infinity, we will get infinity to the power some positive number. So it will become unbounded. Therefore, ROC will not contain z equal to infinity. So basically, when x of n is a finite duration signal, you can assume that the entire z-plane is included in the ROC, but you will have to check for n equal to 0 and n equal to infinity. Let us now solve a problem. We have to find the z transform of delta of n minus 1 and delta of n plus 1. Let us start with delta of n. Its z transform will be summation from n equals minus infinity to infinity delta of n z raised to minus n. But we know delta of n only has magnitude 1 at n equal to 0. Everywhere else it is 0. So we don't really have to take summation from minus infinity to infinity. It only exists at n equal to 0. So we can write the value of delta of n z raised to minus n at n equal to 0. At n equal to 0, delta of n is just 1. Z raised to minus n will become z raised to 0 or 1. So z transform of delta of n is 1 for every value of z. Or it is a finite value for every value of z. So we can say the ROC is entire S-plane. Now let us take delta of n minus 1. Z transform will be summation from n equals minus infinity to infinity delta of n minus 1 z raised to minus n. But then again, delta of n minus 1 is non-zero only at n equal to 1. Everywhere else it is 0. So we don't really have to take the summation from here to here. We can just take the value of this product at n equal to 1. At n equal to 1, we get delta of 0, z raised to minus 1, that is z raised to minus 1. Now, z raised to minus 1 will be a finite value for every value of z except for z equal to 0. If z is 0, this will become 1 by 0, which is unbounded. So we can conclude its ROC is the entire z plane except z equal to 0. Now let us take delta of n plus 1. Z transform will be summation from n equals minus infinity to infinity delta of n plus 1 z raised to minus n. Again, delta of n plus 1 is non-zero only at n equal to minus 1. It is 0 everywhere else. So we don't really have to take the summation. We'll just take this value at n equal to minus 1. So we get z raised to minus of minus 1, which is 1, or simply z. Now, this will be finite for every value of z except z equal to infinity. At z equal to infinity, this will become infinity or unbounded. So we can conclude the ROC is the entire z plane except z equal to infinity. Delta of n minus 1 and delta of n plus 1 are all finite duration signals because they only exist at a single value of n. For the first one, we got ROC to be the entire z plane. For the second one, ROC was the entire z plane except z equal to 0. For the third one, it was the entire z plane except z equal to infinity. Let's go to the next property. According to this, if x of n is a right-sided sequence and if the circle magnitude of z equal to r naught is included in the ROC, then all the finite values of z for which magnitude of z is greater than r naught will also be included in the ROC. Let us take the ROC of a right-sided sequence plotted on a z-plane. For a right-sided sequence, the ROC will always be like magnitude of z is greater than some value, so it will look like this. Since magnitude of z is supposed to be greater than the magnitude of a, the ROC is going to be outside the circle of radius a. Now, assume that a circle of radius 3 is included in the ROC. Now, assume that a circle whose radius is 3 is included in the ROC. Then obviously all the other circles whose radii are greater than 2 are going to be included in the ROC. That is exactly what is written in the property. If the circle with magnitude z equal to r naught is included in the ROC, then all the other circles whose radii are greater than r naught will also be included in the ROC. Let us go to the next property. If x of n is a left-sided sequence and if the circle magnitude of z equal to r naught is in the ROC, then all the finite values of z for which magnitude of z less than r naught will also be in the ROC. For example, let us take the ROC plotted on a z-plane for a left-sided sequence. For a left-sided sequence, we will always get ROC is magnitude of z being less than some value, so it will look like this. If magnitude of z should be less than the magnitude of a, then ROC will be the inner part of the circle whose radius is a. Assume that a circle whose radius is 0.5 is included in the ROC. Then obviously the circles whose radii are less than 0.5, all of them will be included in the ROC. That is exactly what the property says. If the circle magnitude of z equal to r naught is included, then all the finite values of z that is less than r naught will be also included in the ROC. Let us go to the next property. According to this, if x of n is a two-sided signal and if the circle with magnitude z equal to r naught is in the ROC, then the ROC will consist of a ring in the z-plane that includes the circle magnitude of z equal to r naught. First of all, if x of n is a two-sided signal, we'll be able to write it as a summation of a right-sided signal and a left-sided signal. And when we plot the ROC, it will look like this. It will be a ring in the z-plane. And if it includes the circle with magnitude z equal to r naught, then obviously it is going to be included in the ROC like this. Now, to understand why it is a ring in the z-plane, I think it's better to solve a problem. Let us find the z transform of x of n. X of n is b raised to mod n and b is greater than 0. We know magnitude of n can be written as n itself if n is greater than or equal to 0, and it will be minus n if n is less than 0. So b raised to mod n can be written as b raised to n if n is greater than or equal to 0, or b raised to minus n for n being less than 0. Using this idea, we can write x of n like this. X of n will be b raised to n if n is greater than or equal to 0. To show that, let us put a u of n there. Plus, x of n will be b raised to minus n if n is less than 0, or if n is from minus 1 to minus infinity. So let us put a u of minus n minus 1 there. Now, this is a right-sided signal and this is a left-sided signal. And we know how to find the z transform of both of them. For a right-sided signal of the form a raised to n u of n, the z transform is 1 by 1 minus a z inverse, and magnitude of z should be greater than magnitude of a. So for the first part, b raised to n u of n, the z transform is going to be 1 by 1 minus b z inverse, where magnitude of z should be greater than b. For a left-sided signal of the form minus a raised to n u of minus n minus 1, the z transform is 1 by 1 minus a z inverse, and magnitude of z should be less than the magnitude of a. So if we take the function minus b raised to n u of minus n minus 1, we get the z transform 1 by 1 minus b z inverse, and magnitude of z will be less than b. But over here, instead of b raised to n, we have b raised to minus n. B raised to minus n can be written as b raised to minus 1 to the power n. But b raised to minus 1 is 1 by b, so we can write it as 1 by b to the power n. So what we actually have is 1 by b to the power n u of minus n minus 1. This also doesn't have the negative that is required, so we'll have to put it over here. Its z transform is going to be negative of 1 by 1 minus 1 by b z inverse, and magnitude of z should be less than 1 by b. It is given in the question that b is greater than 0, but still we'll have to take two cases. Case 1 is when b is between 0 and 1. In that case, if we plot x of n, this is how it will look like. Let us write x of z. For the first term, we have 1 by 1 minus b z inverse. ROC is magnitude of z should be greater than b. For the second term, we have minus 1 by 1 minus 1 by b z inverse. ROC is magnitude of z should be less than 1 by b. Let us take an example for b. Since b is between 0 and 1, I will take 1 by 3. Then 1 by b will become 3. So according to this, magnitude of z should be greater than b and less than 1 by b. It should be greater than 1 by 3 and less than 3, which is very much possible. So we can write b less than magnitude of z less than 1 by b. If you add these two terms, you will get x of z is equal to b square minus 1 divided by b multiplied by z divided by z minus b multiplied by z minus 1 by b, or b inverse. ROC is b less than magnitude of z less than 1 by b. It is better to write this way so we can easily see the poles and zeros. We have a 0 at z equal to 0. We have a pole at z equal to b. We have another pole at z equal to 1 by b. And ROC will be between b and 1 by b. So if we plot the ROC on a z plane, this is how it will look like. We have a 0 at z equal to 0. We have a pole at z equal to b. We have another pole at z equal to 1 by b. Since b is between 0 and 1, 1 by b is going to be greater than 1. That is why the unit circle is included in the ROC. That is why the unit circle is included in the ROC. Over here, you can see the ROC is actually a ring in the Z plane, just like we saw in the previous property. Let us now take the second case, case 2. Here b is greater than 1. If we plot x of n when b is greater than 1, this is how it will look like. Since b is greater than 1, let us assume a value for b. I will take b is equal to 3. Then 1 by b will be 1 by 3. For the first part, ROC is magnitude of z should be greater than b. So we get magnitude of z should be greater than 3. For the second part, it should be less than 1 by b. So we can write magnitude of z should be less than 1 by 3. But that means magnitude of z should be greater than 3 and less than 1 by 3, which is not possible. Since there is no common ROC between the ROCs of the two parts that make up our signal, Z transform does not exist when B is greater than 1. Let us see the next property. If Z transform X of Z of a signal X of n is rational, then its ROC is bounded by poles or extends to infinity. If the signal is left-sided, ROC will be inside the innermost pole. If the signal is two-sided, it is going to be between two circles. And if the signal is right-sided, it is going to be outside the outermost circle. That is, the ROC will be either bounded by poles or it extends to the infinity. Let's go to the next property. If Z transform X of Z of X of n is rational and if X of n is right-sided, then the ROC is the region in the Z plane outside the outermost pole. So it will look like this. ROC is outside the outermost pole. So obviously Z equal to 0 is not included in the ROC. How about Z equal to infinity? If X of n is causal, then ROC will also include Z equal to infinity. Causal means n can take only values that are greater than or equal to 0. In that case, when we write X of Z is equal to summation from n equals minus infinity to infinity, x of n z raised to minus n can take only values from 0, so let us change the limit. So values of n is always going to be positive. That means power of z is always going to be negative because it is minus n. Therefore, when z becomes infinity, it will be infinity to the power negative something. So it will converge to 0. Therefore, z equal to infinity will be included if x of n is causal. Therefore, z equal to infinity will be included if x of n is a causal signal. We can also observe that poles are closer to the origin than any other point that is in the ROC. The points that are in the ROC are farther away from the origin. Let's go to the next property. If the Z transform X of Z of a signal X of n is rational and if X of n is left-sided, then the ROC is the region in the Z plane inside the innermost pole. So it will look like this. ROC is inside the innermost pole. So obviously Z equal to infinity cannot be included. But we have to check for Z equal to 0. It is written if X of n is anti-causal, then ROC also includes Z equal to 0. Anti-causal means n can take only values that are less than 0. In that case, when we write X of Z, we'll be taking summation from n equals minus infinity to minus 1. X of n, z raised to minus n. In this case, n can only take negative values. So the power of z, which is minus n, is always going to be positive. In that case, when magnitude of z becomes 0, you will get 0 to the power something positive. This is equal to 0, so it is a finite value. Therefore, when x of n is anti-causal, then ROC will also include z equal to 0. What if it is not anti-causal? In that case, n will also take negative values. That means the power of z will also become negative sometimes. So when magnitude of z becomes 0 and the power becomes negative, you will probably get 0 raised to, let us say, minus 1. That will become 1 by 0, which is unbounded. So we can conclude that ROC will also include 0 if x of n is anti-causal, and therefore when n only takes negative values. We can also say that poles of x of z other than any at z equal to 0 are farther from the origin than any other point in the ROC. Obviously, ROC is inside the circle, so any point inside the circle are going to be closer to the origin than any pole because poles are outside the circle. Other than when x of n is not anticausal and z equal to 0 becomes a pole. Let us now solve a problem. We have to find the possible ROCs if x of z is 1 by 1 minus 1 by 3 z inverse multiplied by 1 minus 2 z inverse. To see the zeros and poles properly, let us multiply the denominator and the numerator with z. Then we get x of z is equal to z divided by z minus 1 by 3 multiplied by z minus 2. So obviously we have a 0 at z equal to 0. We have a pole at z equal to 1 by 3, another pole at z equal to 2. Let us plot this on a z plane. There are three options for ROC. Either it can be inside the inner pole, or it can be between the two poles, or it can be outside the outermost pole. In the first case, we will take magnitude of z is less than 1 by 3. In the second case, we will take 1 by 3 less than magnitude of z less than 2. In the third case, we will take magnitude of z is greater than 2. Let us now learn how to find x of n if we have x of z. Or in simple words, inverse z transform. We know x of z is summation from n equals minus infinity to infinity x of n z raised to minus n. But z is r e raised to j omega. So we can write summation from n equals minus infinity to infinity x of n r e raised to j omega to the power minus n. Or we can write it like this: summation from n equals minus infinity to infinity x of n r raised to minus n e raised to minus j omega n. Now, this is the expression to find the Fourier transform of x of n r raised to minus n. So let us write this is equal to Fourier transform of x of n r raised to minus n. That is, we got x of z or x of r e raised to j omega is equal to Fourier transform of x of n r raised to minus n. That must mean x of n r raised to minus n is equal to inverse Fourier transform of x of r e raised to j omega. Let us take the r raised to minus n to the other side. It will become r raised to n. Then we get x of n is equal to r raised to n multiplied by inverse Fourier transform of x of r e raised to j omega. This is the idea from which we are going to build inverse z transform. Let us use the expression for inverse Fourier transform. Then x of n will become r raised to n multiplied by 1 by 2 pi integral over an interval of 2 pi x of r e raised to j omega e raised to j omega n d omega. Let us bring r raised to n inside the integral and put it over here. Then we get 1 by 2 pi integral over an interval of 2 pi x of r e raised to j omega r raised to n e raised to j omega n d omega. We have r raised to n e raised to j omega n. This can be written as r e raised to j omega the whole to the power n. Let us replace it that way. Now we are taking z equals r e raised to j omega. If we differentiate both sides, we get dz is equal to r is a constant. Derivative of e raised to j omega with respect to omega will be e raised to j omega multiplied by j d omega. But r e raised to j omega is just z. So we can write this is equal to z j d omega. Therefore, d omega will be dz divided by jz. Let us now modify this equation accordingly. We get x of n is equal to 1 by 2 pi. When we are talking in terms of omega, integration is across 2 pi, but we are going to talk in terms of z. If omega can take any value from 0 degree to 360 degree, then in the z plane we'll be taking the entire circle. So we will use the circular integral, which means we're integrating throughout the contour of the circle. X of r e raised to j omega will become x of z. R e raised to j omega to the power n will become z raised to n. D omega becomes dz by jz. So we can write dz by jz. Let us take the j from here and put it with 2 pi because it's a constant. We have a z raised to n divided by z. It will become z raised to n minus 1. So finally we get x of n is equal to 1 by 2 pi j closed integral of x of z raised to n minus 1 dz. This is the equation for inverse z transform. Let us put it in a box. But just like we did in the Laplace transform, we will not be using this expression to find the inverse z transform. We will use other ways to do that. For example, we can use the same partial fraction expansion method for a rational function x of z. First, we will compute the poles of x of z. Then we will consider what is the ROC. Then we will use partial fraction expansion to expand x of z in this form. And then we will find inverse z transform based on the results that we already know. Let us solve a problem like that. We have to find x of n if its z transform is of the form 3 minus 5 by 6 z inverse divided by 1 minus 1 by 4 z inverse into 1 minus 1 by 3 z inverse. Here ROC is given, magnitude of z is greater than 1 by 3. Let us locate the poles of x of z. If z is equal to 1 by 4, this part will become 0, so z equal to 1 by 4 is a pole. If z is equal to 1 by 3, this part will become 0, so z equals 1 by 3 is also a pole. In the question, it is given magnitude of z should be greater than 1 by 3. Out of 1 by 4 and 1 by 3, 1 by 3 is the outermost pole. So here ROC is outside the outermost pole. So we can say x of n is right-sided. Now let us use partial fraction expansion to write x of z in this form. A by 1 minus 1 by 4 z inverse plus b by 1 minus 1 by 3 z inverse. By using the same method we used in the Laplace transform, a will be equal to limit z tends to the pole 1 by 4, 1 minus 1 by 4 z inverse multiplied by x of z. That is limit z tends to the pole 1 by 4. If you multiply x of z with 1 minus 1 by 4 z inverse, this will be cancelled. So we get 3 minus 5 by 6 z inverse divided by 1 minus 1 by 3 z inverse. Here if you give z equal to 1 by 4, this will simplify to 1. So a is 1. Now let's try to find out b. B will be limit z tends to the pole corresponding to b, which is 1 by 3. 1 minus 1 by 3 z inverse multiplied by x of z. x of z is over here. If you multiply it with 1 minus 1 by 3 z inverse, this will get cancelled. So we get limit z tends to 1 by 3. 3 minus 5 by 6 z inverse divided by 1 minus 1 by 4 z inverse. If you give z equal to 1 by 3 here, this will become 2. So b is 2. Therefore, x of z becomes 1 by 1 minus 1 by 4 z inverse plus 2 by 1 minus 1 by 3 z inverse. ROC is magnitude of z greater than 1 by 3. So both of these should have inverses that are right-sided. Let us use the result that we already know. 1 by 1 minus a z inverse when magnitude of z is greater than magnitude of a is the z transform of a raised to n u of n. So we can write x of n is going to be inverse z transform of 1 by 1 minus 1 by 4 z inverse will be 1 by 4 raised to n u of n plus 2 times inverse z transform of 1 by 1 minus 1 by 3 z inverse will be 1 by 3 to the power n u of n. Or we can write x of n is equal to 1 by 4 to the power n plus 2 times 1 by 3 to the power n multiplied by u of n. Let us go to the next problem. We have to find x of n. X of z is given. This is the same x of z from the previous problem. But ROC is different. So we can use the same partial fraction expansion with the new ROC. Let us call the inverse of the first part x1 of n. x1 of n will be the inverse z transform of 1 by 1 minus 1 by 4 z inverse, where magnitude of z is greater than 1 by 4. Let's call the inverse of the second part x2 of n. Then x2 of n will be the inverse z transform of 2 by 1 minus 1 by 3 z inverse. And magnitude of z is less than 1 by 3. So the first part is right-sided, the second part is left-sided. Since x1 of n is a right-sided sequence, we can write x1 of n is going to be 1 by 4 to the power n u of n. Since x2 of n is left-sided, we can write x2 of n is going to be minus 2 times 1 by 3 to the power n u of minus n minus 1. Putting them together, we can write our final answer x of n. X of n will be 1 by 4 to the power n u of n minus 2 times 1 by 3 to the power n u of minus n minus 1. Let's go to the next problem. Here again we have the same x of z but with a new ROC. Magnitude of z is less than 1 by 4. So we can use our same partial fraction expansion with the new ROC. Let us again take x1 of n to be the inverse z transform of the first part. ROC is going to be magnitude of z is less than 1 by 4. So x1 of n is a left-sided sequence. We can write x1 of n is equal to minus 1 by 4 to the power n u of minus n minus 1. Let us take x2 of n to be the inverse z transform of the second part. ROC is magnitude of z being less than 1 by 4. But if magnitude of z is less than 1 by 4, it is going to be less than 1 by 3 also, because 1 by 3 is greater than 1 by 4. So we can write magnitude of z is less than 1 by 3 also. That means x2 of n is also a left-sided sequence. So we can write x2 of n is minus 2 1 by 3 to the power n u of minus n minus 1. To get the final x of n, we can put them together. We will get minus 1 by 4 to the power n u of minus n minus 1 minus 2 1 by 3 to the power n u of minus n minus 1. Let us now learn a new way of finding inverse z transform. Here x of z is given in this form 4z square plus 2 plus 3z inverse. Magnitude of z can take any value from 0 to infinity. Magnitude of z can take any value between 0 and infinity. This makes sense because we know x of z is given as summation from n equals minus infinity to infinity x of n z raised to minus n. That is, it starts from minus infinity, so I'll put 3 dots. If you give n equal to minus 1, you get x of minus 1 z raised to 1 plus for n equal to 0, you get x of 0 z raised to 0 plus if you give n equal to 1, you get x of 1 z raised to minus 1 plus infinite terms more. So what this means is the coefficient of z raised to 1 is going to be x of minus 1. Coefficient of z raised to 0 or the constant term is going to be x of 0. Coefficient of z raised to minus 1 will be x of 1. So looking over here, we can see 4 is going to be x of minus 2, 2 is going to be x of 0, 3 is going to be x of 1. Only these three terms are available. So we can say for any other value of n that is not equal to minus 2, 0 or 1, x of n is going to be 0. So x of n is 3 when n is equal to 1. X of n is 2 when n is equal to 0. X of n is 4 when n is equal to minus 2. We know how to write it mathematically. We can write x of n is equal to 4 at n equal to minus 2. To show that, we'll multiply 4 with delta of n plus 2 plus it is 2 at n equal to 0. To show that, we'll multiply the 2 with delta of n plus it is 3 at n equal to 1. To show that, we'll multiply 3 with delta of n minus 1. So the inverse Z transform of 4z square plus 2 plus 3z inverse is 4 delta of n plus 2 plus 2 delta of n plus 3 delta of n minus 1. Let us learn one more method of finding inverse Z transform. Here we have to find x of n if x of z is 1 by 1 minus a z inverse, where magnitude of z is greater than magnitude of a. We already know its answer. It is a raised to n u of n. But let us try to derive it in a new method. We will be doing it by using long division. This is 1 divided by 1 minus az inverse. So let us write 1 divided by 1 minus az inverse. 1 divided by 1 is 1. So 1 multiplied by 1 minus az inverse. 1 minus 1 is 0. 0 minus minus az inverse is plus az inverse. Now az inverse divided by 1 is plus az inverse. Az inverse multiplied by 1 minus az inverse will give us az inverse minus a square z raised to minus 2. Subtracting az inverse from az inverse, we get 0. Subtracting minus a square z raised to minus 2 from 0, we get plus a square z raised to minus 2. Now, a square z raised to minus 2 divided by 1 is plus a square z raised to minus 2. This will go on like that. So we get 1 by 1 minus a z inverse is equal to 1 plus a z inverse plus a square z raised to minus 2 plus up to infinite terms. So basically, this is a geometric progression with infinite terms. Its first term is 1. Its common ratio is a z inverse. For an infinite geometric progression to converge to a finite value, its common ratio should be less than 1. So this will converge if magnitude of a z inverse is less than 1 or magnitude of z is greater than magnitude of a. This condition is already given in the question, so we are good to go. So 1 by 1 minus a z inverse is 1 plus a z inverse plus a square z raised to minus 2, etc. But we already learned the constant term is x of 0. So we can write x of 0 is 1. Coefficient of z inverse will be x of 1. So x of 1 is a. Coefficient of z raised to minus 2 will be x of 2. So x of 2 is a square. So basically I can see x of n is going to be a raised to n. But there is a problem. N is only taking values that are positive, right? We only have values like 1, z inverse, z raised to minus 2, etc. There is no z or z square or z cube. So this is only applicable if n is greater than or equal to 0. So to show that, along with a raised to n, I will also put a u of n. Therefore, the inverse of 1 by 1 minus a z inverse, if magnitude of z is greater than magnitude of a, is a raised to n u of n. Let us solve one final problem. We have to find x of n. If x of z is 1 by 1 minus a z inverse, magnitude of z is less than magnitude of a. We also know the answer to this. It is minus a raised to n u of minus n minus 1. But let us figure it out using our new method. Let us use long division. We will use long division. We have to calculate 1 divided by 1 minus a z inverse. But there is a difference here. Here magnitude of z is less than magnitude of a. If you bring magnitude of z to this side, we get magnitude of a z inverse is greater than 1. So magnitude of a z inverse is greater than 1, which means we have to write minus a z inverse first and then 1. Let us change it. So we are dividing 1 with minus a z inverse plus 1. 1 divided by minus a z inverse will be minus a inverse z. Minus a inverse z multiplied by minus a z inverse is 1. Minus a inverse z multiplied by 1 is minus a inverse z. 1 minus 1 is 0. 0 minus minus a inverse z is plus a inverse z. Now, a inverse z divided by minus a z inverse. That will become minus a raised to minus 2 z raised to 2. Again, a raised to minus 2 z raised to 2 multiplied by minus a z inverse will become a inverse z. Minus a raised to minus 2 z square multiplied by 1 will become minus a to the power minus 2 z to the power 2. Subtracting, we get 0 plus a raised to minus 2 z raised to 2. Again, if we divide a raised to minus 2 z square by minus a z inverse, we will get minus a raised to minus 3 z cube. This goes on like that. So we can write 1 by 1 minus a z inverse. If magnitude of z is less than magnitude of a will be equal to minus a inverse z minus a raised to minus 2 z square minus a raised to minus 3 z cube plus up to infinite terms like that. Let us check the region of convergence. This is a geometric progression. Its first term is minus a raised to minus 1 z. Second term is minus a raised to minus 2 z square. This is actually the first term multiplied by a raised to minus 1 z. So its common ratio is also a raised to minus 1 z. So this will converge to a finite value if the magnitude of the common ratio a raised to minus 1 z is less than 1. Or we can say magnitude of z is less than the magnitude of a. This is exactly the condition we have in the question, so we are good to go. Now let us compare. Coefficient of z is minus a inverse. We know coefficient of z is x of minus 1. So x of minus 1 is minus a inverse. Coefficient of z square is x of 2. Coefficient of z square is x of minus 2. So we get x of minus 2 is minus a raised to minus 2. Coefficient of z cube is x of minus 3. So we get x of minus 3 is minus a raised to minus 3. It goes on like that. So we can write the nth term x of n is going to be minus a raised to n. But there is one problem. We only have terms where n is equal to minus 1, minus 2, minus 3, etc. Only the negative numbers from minus 1 to minus infinity. For any positive value of n or for n being 0, x of n is 0. So to show that, we have to multiply minus a raised to n with u of minus n minus 1. A final question, why are we writing u of minus n minus 1? Why can't we just write u of minus n? The reason is very simple. If you write u of minus n, you are essentially including n equal to 0 also. But we only need to take n from minus 1. So we have to shift u of minus n 1 units towards the left. That is why we are writing u of minus of n plus 1. That is u of minus n shifted 1 units towards the left. That's all about it for today. See you in the next video. And don't forget to subscribe.